Hello everyone. In this video, we are going to look at comparing two qualitative variables using two-way tables, also called contingency tables, or even referred to as a cross-tabulation. You simply have a table with rows and columns. The columns are assumed to be your independent variable. So our independent variable is degree of job pressure. The rows are the dependent variable, in this case, age in years. So what we have here is a contingency table showing the degree of job pressure, low, medium, or high, in different age groups, less than 25, 25 up to 40, 40 up to 60, 60 and older. There are a grand total of 500 people represented in this table. 60 of them were less than 25, 140 of them were age 25 up to 40, 180 were age 40 up to 60, and 120 were age 60 or older. Also of these 500, 162 reported low degree of job pressure, 170 reported medium degree of job pressure, and 168 reported high degree of job pressure. So here we have the column totals, and here we have, here we have row totals. All right, so here is our contingency table. What we're going to do from this is compute empirical probabilities. They're empirical probabilities because it's from collected data. It's not theoretical, but computed from collected data. You can also think of these as relative frequency approximations to probability, right? So they are approximations based on data. Empirical, based on data, meaning relative frequency approximations. So let's look at some of these. So the probability that someone in this table is less than 25 years old. Well, that's straightforward, right? Because there are 60 individuals who are less than 25 years old out of a total of 500 individuals. So that gives us 0.12, or 12% of the people represented in the table were less than 25 years old. This would be considered a marginal probability. All right, this would be a marginal probability. Probability of high job pressure. Again, straightforward. There are a total of 168 individuals who reported high job pressure out of a total of 500 individuals. So 0.336. Let's see, number 3, the probability of less than 25 and high. Aha, here we have a joint probability, because we're asking about two things at once. Well, if you're asking two things at once, you have a row value and a column value. So the row less than 25, the column high. So we're looking at this value here that is in both the row less than 25 and the column for high. So less than 25 and high are 22 individuals out of the 500. 0.044, and that is referred to as a joint probability. Here's another joint probability with an and. 40 to 60 and medium. All right, so 40 to 60 and medium has this cell right here. So 40 up to 60 and medium job pressure, 63 individuals. So this joint probability is the 63 out of the 500 individuals. Now this one we're looking at, the probability of 40 to 60 given high. Oh, we're given some information. So this is a conditional probability because the probability is based upon the condition the individual reported a high job pressure. So we are just focused on this single column. So when you have a given, what is given then is a particular column or even a row. So essentially your sample space has been shrunk down to that particular column or row. So in this example, our sample space is only the high column because we are given the individual reported high job pressure. So out of these 168 individuals, the age group 40 to 60, okay, is 59. So 59 of these 168 individuals, all right, so were 40 to 60. So 59 were 40 to 60 out of the 168 individuals that reported high job pressure. So whenever you have a given and a conditional probability, the sample size is shrunk to just the total corresponding to the given category. So from the highs, we have 59 that are 40 to 60 out of the 168 that reported high job pressure. 0.3512, rounded off. Okay, so that is a conditional probability. Number 6 here, we have the probability of high given 40 to 60. Again, a conditional probability, but this time what's given is the age group. So we are given a category for age, an age category. So our sample space has shrunk down to this single row. So we are only interested in the 180 individuals in the 40 to 60 age group. Of those 180 individuals, the number that reported high job pressure is 59. So we get equals 59 out of the 180. Notice that the numerators between these two conditional probabilities are both D9. They're both the value 59 because that is in the intersection of these two categories. What's different is the denominator. Here the denominator is D11, the total for the high column, because we were given the individual reported a high job pressure. And on this one, the denominator was the 180, or the total for 50 up to 60 age group, because we were given the age group 40 to 60. So whenever you have a given, you're going to want in the numerator the cell that's in the intersection of the two categories, but the denominator will be what comes after the given. The denominator is always the total for either the column or row category that comes after the given. So just think of the given as like your fraction bar, and then here is your denominator. So numerator is the intersection, given, denominator. Let's look at one more, actually a couple more of these givens. The probability of less than 25 given low. So we are given low degree of job pressure, so the denominator will be 162, and we're interested in the age group less than 25, so that is here. 20 or less than 25 out of the 162 individuals. So let's type equals And even though I can't see the cell in the window, I can see what I'm inputting up here. So we want the 20 out of the 162. So B7 out of B11. So this is the probability the individual was less than 25 years old, given they reported a low degree of job pressure, right? Less than 25 and low, given low. 0.1, 2, 3, 4, 5, 6. Wow, that's interesting. Okay, so 0.1, 2, 3. Now we want the probability of medium given 60 plus. So this time we are given an age group, so we are confined to this row here for the 60 plus individuals. So out of these 120 60 plus individuals, 43 reported medium job pressure. Okay, 43 reported medium job pressure. So the probability here is the 43 60 and older individuals, of which there are 120 who reported medium job pressure. So C10 out of E10, 0.3583. Now we're going to look at some different examples. These last three examples all contain the word or, all right? So here we are going to be adding. Or always implies the addition rule. So what we are going to be using here is the generalized addition rule. Basically, this tells us that we need to avoid double counting, and this is why. 60 or high. So let's see, how many of them were in the 60 plus category? Well, 60 plus, there's 120 individuals. We can add to that the number in the high category. How many in the high category? 168. So we've added these two totals. But notice in doing so, this number 43 that is in both the 60 and older row and the high column was included twice. This 43 was included in the 120. This 43 was also included in the 168. So we have double counted the 43. Therefore, we need to subtract it out. So I'm going to subtract the 43. Now I can close the parenthesis, okay, and divide by the grand total. So when we're doing these OR problems and using the generalized addition rule to avoid double counting, we're always going to have row total plus column total minus the intersection of the row and column. And then that sum will be divided by the grand total. What's neat is that when you're working with the table and clicking in here, because we have a column, a row, and the value in the intersection, and then the grand total is always here in the bottom right, we're always going to have a square here. These cells will always form like the vertices of a rectangle, So if something is out of line, you've clicked the wrong value. This probability ends up being 0.49, 49%. Let's do two more of these examples. So here's another OR one. So equals, open parenthesis, 25 to 40 or medium. So 25 to 40 is this row of 140 individuals plus medium, which is this column of 170 individuals. But now we subtract this intersection of 46 individuals that was counted in both the age row and the job pressure column. Close our parenthesis and divide by the grand total of 500. We can see what I did up here, and we see that we do indeed have vertices creating a rectangle, So now when we hit enter, we see it's 0.528. One more of these equals, open parenthesis, 40 to 60 or low. 40 to 60, the total in the 40 to 60 age group is 180, plus the total in the low category, 162, subtract the value in the intersection of the age row and pressure column is 58. Subtract that out because it was double counted. Close the parenthesis, then divide by the grand total of 500. Again, note that the cells form the vertices of a rectangle. And then when we hit enter, 0.568. So these are the different kinds of probabilities you will encounter. These marginal probabilities, which are simply probabilities based on one of the categories, either a single row category or a single column category. The joint probabilities, which contain and so are intersections of a row and a column. So the numerator is an intersection. These then all have denominators of the grand total. The OR problems that use the generalized addition rule also have denominators that are the grand total. And with OR now we are adding. What we're doing here is the numerator is your row total plus the column total, but we counted the intersection twice, so we subtract the intersection, then we divide everything by the grand total. Right. The only probabilities that have a denominator different from the grand total are the conditional probabilities, all right? The conditional probabilities have the given, or they're worded in such a way that you know you are only interested in a single row or a single column. I like to write them with givens. You often see them this way, but I could have said, for example, that of those who reported a high level of job pressure, how many of them were in the 40 to 60 category, right? Of those who reported low job pressure, how many were less than 25? Of those over 60, how many reported medium job pressure? So those are the empirical probabilities. The last thing I want to show you is cross-tabulation analysis. And in here, we're actually just looking for conditional probabilities given specific columns. So for cross-tabulation analysis, we want to find these column percentages. So here, this column percentage, we have 20 out of 162, and because we want it as a percentage, we'll multiply by 100. I can make this a formula if I put the dollar signs around the denominator, because that won't change, but the numerator will change. So 12.3% for less than 25, and 20.98% for 60 and older. So notice these are the percentages of the independent variable, in this case low, that were in each of the dependent variables, so each row category. So 12.3% of those who reported low job pressure were less than 25. 30.86% of those who reported low job pressure were 25 to 40 years old. 35.8% of those reporting job pressure were 40 to 60 years old, and 20.987 of those reporting low job pressure were 60 and older. Of course, these percentages had better add up to 100, and indeed they do. So we're going to do that for each of the categories. I'm going to go ahead and highlight the percentage columns so we can stay focused on the percentages when we talk about or compare these values to one another in our cross-table tabulation analysis. So let's find the column percentages for medium job pressure. So that equals 18 out of the 170 total. I will click the F4 on my PC to insert the dollar signs so that stays fixed when I copy the formula, times the 100 to change it into a percentage. So we get 10.588. I copy these down to have 27.058, 37.058, 25.294. And I always love to do these double checks, make sure I have the 100% here. So here are the column percentages for medium degree pressure. Now for the high degree of job pressure, the column percentages, we have our 22 divided by the 168 column total. Fix it with the dollar signs. Okay. So let's, what was I doing here? Yes, I was trying to hit F4. There we go, to get the dollar signs, and then multiplying by 100, 13.09%, copy that down, 26.19, 35.119, 25.595 should add up to 100%, and it does. So cross-tabulation analysis, we want to find the column percentages, and then we want to compare them across the rows to see if they look similar or not. If they are similar across the row, then we would say that the variables are independent because it didn't matter which age group, all right? Or we should say it didn't matter which level of degree job pressure, it was similar across the age group. So every degree of job pressure was similar across the age group. 12, 10, 13 looks similar. 30, 27, 26 looks similar. 35, 37, 35 looks similar. 20, 25, 25. Again, these look similar, so it suggests that these are independent. Degree of job pressure is independent of age group. Now the largest difference, here we got like from 10.5 to 13, right? That's a difference of, about 2.5. Here, 26 to 30, but 26.2 to 30.8, we're looking about a 4.4 difference. Here, let's see, 37, I'll just say 0.1 to 35.8, about a 1.7 difference. And here, let's say 21 to about 25.5, really 25.6. So this one's more. This is like 4.5. Yeah, 4.5, because that would be 21, 4.5 closer. All right. So they seem to be similar. So I would say here that they appear similar. By how much? I think the greatest we had was at most 4.5%. Of course, that was just estimating. And since they are similar, they appear to be independent. So this is cross-tabulation analysis. Notice it's a little bit subjective because what is similar? It is best to determine independence by using a chi-squared test of independence, which I have another video describing. And when I did that, we did indeed conclude that the row and column variables were independent. But this is a more formal way of doing it. Crunching the numbers is a lot better than simply looking across and seeing at most how much do they differ. But this then is a basic cross-tabulation analysis. So that concludes my discussion of cross-tabulation, working with contingency tables, also called two-way tables, in which we compare two qualitative variables, and we looked at empirical probabilities, column percentages, and seeing whether they appeared similar or not. Thank you for watching.